Hi, this video is talking about the common pitfall I saw in my previous students. So just give everybody a heads up. This will be something you want to be watching out for. So ideal gas equation we learned it's PV equal to MRT. And when do we use it? That's where we're gonna focus on today. So previously we talking about ideal gas. It's when those gas molecules are spread apart. They don't touch each other. So it's gonna be low pressure and also high temperature. And in terms of how low of pressure and how high of a temperature, then we're using this concept called a reduced temperature, and it has a symbol TR. And then TR is defined as the given temperature divided by critical temperature. Okay, the same concept will have called the reduced pressure. Reduced pressure, that's going to be PR. And PR is going to be the given pressure divided by the critical pressure, right? So where do we get the critical temperature and the critical pressure? In one of the videos called the phase diagram, you're talking about the critical temperature and critical pressure. It's when the liquid and gas become indistinguishable and they become one state. It's hard to comprehend, and because that's some pressure and temperature we don't normally see. For example, where do we get this critical temperature and pressure? That's from table A1. Let's take a look at it. At table A1, I'm sorry. Yeah, it is on table A1. There's critical point property. For example, air, that's going to be the critical temperature, and that's going to be the critical pressure. Okay. So we are going to using, you might look at this. This pressure is 3.77 megapascal. Then we're going to compare that with given pressure and given temperature compared to this critical temperature. And so here's the criteria. When this PR, this reduced pressure, if it's less than 10, because we want the pressure to be low, right? If this is less than 10 and at the same time this is going to be concurrent criteria. If this TR is going to be greater than 2, if they meet this criteria, then they're going to be considered as ideal gas. If they are considered as ideal gas, then we can use this equation PV equal to MRT, ideal gas equation. The second possible so if either they satisfy the first conditions, or if they have this PR itself, it's very small, the pressure is so small, it's less than 1, then they also consider as ideal gas equation. Then they can use PV equal to MRT. That's how we scientifically determine if we can use PV equal to MRT or not. But let's just talking about a reality. We don't normally go ahead to do this exercise, and here is some common observation. Often in thermodynamics, if you have air, if you have nitrogen, because air is made of 2/3 of nitrogen, right? And then you may have oxygen. All of those, they're gonna consider as ideal gas in our thermodynamics class. And which one will not be considered as ideal gas? Which is water, vapor, normally not considered as ideal gas. R134, the freon, they are normally not ideal gas. All right, so that's very important to use. The reason I want to focus on this is Remember previous videos, we learned so much about steam table, learned so much about R134 table, and we're looking at those three different phase compressed liquid, saturated liquid, vapor mixture, and superheated vapor. None of those are ideal gas, right? Okay, those tables are tabulated from the experiment data. Now we just introduce this ideal gas concept. It's just one equation, PV equal to MRT. And a lot of us will naturally say, oh, we're just going to use PV equal to MRT to solve every single problem. However, that's wrong. For water, R134, you cannot use PV equal to MRT. And I'm going to put a big X on there. And instead, what we're going to do, we're going to look at our tables because they are not ideal gas. Okay? So don't go ahead and use PV equal to MRT for every single problem because that's not right. That PV equal to MRT only for ideal gas. Okay? So that's all I want to focus on. So try to avoid that pitfall. All right, see you next time. Bye.